Perfect. Who was already in the session from me? So a lot of people, almost everyone. That's perfect. So I don't talk too much about me anymore. Welcome to my session about joins in SQL Server. In the next 90 minutes, I want to give you a very detailed overview about joins in SQL Server. In the first step, we will talk about how SQL Server executes our joins on the physical level. Means we will see which physical join operators SQL Server can use in the physical execution plan, mainly nested loop, merge join, and hash join. And based on that foundation, we will look on the logical joins, cross join, inner join, and outer join, how they are translated to the physical level, and if time permits, I also want to talk a little bit more in detail about subqueries, because a subquery, as we will see later in the execution plan, is nothing more than a join between two tables. Before I talk about the physical join operators, I want to give you here a very brief overview what happens in SQL Server when we execute a query. In the first step, SQL Server has to parse our query, means SQL Server checks if we have syntactical errors, SQL Server checks if we reference tables that are existing in our current database, if we reference columns which are part of those tables. In the next step, a so-called normalization phase occurs, and within the normalization phase, SQL Server generates a so-called query tree out of our logical SQL statement. We'll see later what a query tree in SQL Server looks like. That query tree is handed over to the query optimizer, and the query optimizer generates our physical execution plan. Means we will also see in the physical execution plan which physical join operator SQL Server has chosen for our logical join, in which order SQL Server joins both tables together. So for example, you can make a join between table A and B, or also between table B and A. Afterwards, when SQL Server has generated our physical execution plan, the execution plan gets cached in the plan cache for further reuse. Then SQL Server allocates memory for our execution plan, and when that memory allocation was granted to our query, then SQL Server can finally execute the query itself. You can already see from the beginning, when we submit the query to SQL Server to its final execution, it's a very, very long way and time in SQL Server. Imagine we have a simple query where we join two tables together, where we have a filter predicate. As I've said in the first step, during that normalization phase, SQL Server generates out of that logical query a so-called query tree. It's just a tree structure, and within that query tree structure, SQL Server still shows our logical query. As you can see, we have a join between table A and P, and we have finally a filter where we eliminate some non-qualifying rows, and finally we make a so-called projection where we just select specific columns from both tables. That query tree is handed over to the query optimizer, and the query optimizer generates finally our physical execution plan, and that execution plan is finally executed. Execution plan is very, very important, because only the execution plan tells you what happens during runtime. The SQL statement that we are writing is just a logical expression. We just tell SQL Server how our result should look like, but only the execution plan tells us what happens during runtime and why, for example, our query is slow or why our query is so fast. Let's talk now about the physical join operators that SQL Server implements. SQL Server implements 3 different physical join operators, a so-called nested loop operator, a so-called merge join, and a so-called hash join. I want to demonstrate you now on the flip chart all 3 join operators that SQL Server implements. Imagine we have a table A, we have a table B, and we want to perform a join between both tables. Imagine we make a join like on A.id equals B.id, so we have here some ID values. Let's say we have 3, 2, 1, 5, 7, 1, 2, and we have here in the second table some values 5, 7, 8, 1, 2, 5, and 3. When we look at our execution plan, we can see that SQL Server references both tables, table A, table B, and finally makes a nested loop join between both tables and returns those rows which are qualified in that join condition. The nested loop operator in SQL Server is mainly a for each operator, for each row. Internally, SQL Server operates with 2 loops which are just nested inside. Means SQL Server starts the outer loop over the outer table, like table A here, takes the first record, now it has the value of 3, and loops an inner loop over the inner table and checks if we have qualifying rows. In our case, we have a row value of 3, so we return that row to the next operator in the execution plan. Then we move forward in our outer loop, value of 2, and for the value of 2, we are scanning again the complete table to find again qualifying rows. Means the inner loop is executed for every record that we have in the outer table. So imagine when you have in the outer table, let's say 100 rows, then SQL Server has to execute the inner side 100 times for every record over and over and over again. Means as a conclusion, the query optimizer mainly uses the nested loop operator when he identifies one table with just a few records based on the statistics. Means when you have inaccurate statistics and the query optimizer estimates one row and in reality we are getting back 100 rows, we have some performance problems. So that's very, very important. The physical join operator like nested loop, merge join, hash join is always chosen based on our statistics. Means when we have inaccurate statistics, we have a problem. And the query optimizer is also able to rearrange those tables. So for example, when we talk about inner joins, an inner join between table A and B is the same as an inner join between table B and A. We will see that later. With that inner join reordering, the query optimizer is just, or the query optimizer is able to use that table as the outer table, which has the least amount of rows. Again, based on the statistics. So let's switch over to SQL Server and let's have a look on the nested loop operator. I have here a simple join between 2 tables, table sales order header, sales order detail. As you can see, when we look at the execution plan, we have the nested loop operator as the physical join operator. In our case, the outer table is the table sales order header, and the inner table is the table sales order detail. We have here very, very good statistics. You can see SQL Server estimated one row, estimated numbers of rows is 1, and in reality, actual numbers of rows, we also just returned one row. Therefore, SQL Server also has chosen that table as the outer table. And the inner table is the table sales order detail, and you can see the inner side was also only executed once. Number of executions, 1. Okay? When you have an execution plan where SQL Server has to introduce a bookmark lookup, I've already talked yesterday about bookmark lookups, then that bookmark lookup is always implemented with the nested loop operator. It's also very, very important because the bookmark lookup has to be done for every record from that non-clustered index that we are finding. Therefore, SQL Server always introduces here a nested loop operator. Who of you uses table variables in SQL Server? Table variables have one large problem. Which one? We have no statistics on table variables, means the query optimizer hard-coded guesses one row. It's not really a guess, it's just a hard-coded value. So for example, when I declare here a table variable, I insert here 20,000 rows, and I make a join with a different table. In that case, we already know how the physical execution plan of that join looks like. We have a nested loop operator, and SQL Server has chosen as the outer table our table variable because we have an estimation of one row. As you can see, the outer table is our table variable with an estimation of one row, and in reality we are returning more than 14,000 rows. Means the inner side, in our case the clustered index seek on the table person, was executed 14,700 times for every record that we get from the outer table. Just think about that. So table variables only make sense when you are dealing with a small amount of records. When you deal with a larger amount of records, use temp tables, because with temp tables we have accurate statistics. So table variables and temp tables have different use cases in SQL Server. So for example, when I see a query in front of me, that query is slow, and I see that that query uses table variables, in the first step, just try to rewrite that query with a temp table. When it's faster, you know why. Because the table variable has no associated statistics. So that's one of the drawbacks that you see with table variables. Questions on that so far? Perfect. Let's move on. The next physical join operator that SQL Server implements is the so-called merge join. Imagine again, we have again our two tables. Table A with some ID values and table B with some ID values. The first prerequisite for a merge join is sorted input. So when we look now on both tables, we have here sorted input. Same with the second table. When we look at the execution plan, query optimizer chooses one table as the outer table, the other table as the inner table, and we perform our merge join. Merge join is very, very simple. SQL Server takes the outer table, in our case table A, and just moves now between both tables just forward. So as you can see, a merge join is very, very efficient because you are just reading from every table just once and you can retrieve your result very, very fast. As I've said, the prerequisite for a merge join is sorted input. How can you achieve sorted input for a merge join? Sorry? Join on indexed columns means when we have here index, clustered index, non-clustered index, then we provide sorted input. It can be also the case that the query optimizer introduces an explicit sort operator. You can also see executing like that. Means SQL Server pre-sorts table A and makes afterwards an efficient merge join with the table B, where we have maybe already pre-sorted input because we have read the data from a clustered or non-clustered index. So in that case, very, very simple, SQL Server just pre-sorts the data. The problem is the sort operator needs a so-called memory grant. A sort space. You need some space, some memory to perform that merge sort algorithm that SQL Server implements here. The size of that memory grant is based on our statistics. Means when our statistics are again inaccurate, SQL Server estimates too less query memory, means that memory grant is just too less, and in that case the sort operator spills over to the public toilet of SQL Server. TempDB means your sort operator, which is normally very, very fast because it's just in memory, happens physically inside your TempDB. Just think about that. Let's have a look on that. I create here a first table. I insert 1,500 rows. I create another table and also insert 1,500 rows into that table. So we have just two tables with 1,500 rows. As you can see, we have on column 2 unique values. There are no duplicate values in both tables, just unique values. Normally, the query optimizer takes as an outer table that has unique values. But here, the query optimizer has no idea about that uniqueness because we haven't created any unique constraint or any unique non-clustered index. Means the SQL Server query optimizer doesn't know about that uniqueness, which is not interesting. What I'm doing here, I make a join between both tables. By default, SQL Server isn't choosing the merge join. It wouldn't be here the best physical join operator. In that case, I'm just hinting SQL Server for the merge join with an option merge join. Means we have now our merge join, and because we need sorted input on column 2 on both tables, SQL Server introduces a sort operator on both inputs so that the merge join is fed with sorted input. As you can also see on the select operator, we have here a memory grant. We need here 1 megabyte of query memory, which is used internally for the sort space of the sort operator. In the next step, I create a unique non-clustered index on the second table. Means now the query optimizer knows, hey, we have unique values in the second column of the second table. And therefore, the query optimizer will rearrange both tables. Means later on, the outer table is the second table, and the inner table is the first table, and one of the sort operator will disappear because we are already reading pre-sorted from that non-clustered index. Means in that case we can also run that query without any query hint, and the query optimizer itself already chooses the merge join. Just think about that. And the sort operator disappeared. SQL Server has rearranged our tables. Now table 2 is the outer table, table 1 is the inner table. And finally, when we create on the other table also a unique non-clustered index, the other sort operator also just disappears. Means when you have on those join columns non-clustered indexes, then the query optimizer is able to introduce a merge join as the physical join operator. And as we have seen, a merge join is very, very efficient because we are just reading both sets, both tables, just once forward. With the nested loop, we have seen the inner side was evaluated over and over and over and over again. Means a nested loop never ever scales. A merge join scales very, very well. Make sense? And the hash join is the third join operator which SQL Server implements on the physical level. Imagine again we have both of our tables, table A, table B. Again we have some input values. Table B. When we look at the execution line, again, SQL Server accesses both tables and performs a hash join between both tables. A hash join always consists of two different phases. The first phase is a so-called build phase, and the second phase is the so-called prove phase. The first phase, in the build phase, SQL Server takes the outer table, again the smallest table based on our statistics, and creates a so-called hash table. And within that hash table, we have multiple hash buckets. So what SQL Server is doing, SQL Server just distributes our data across those hash buckets. SQL Server uses here undocumented hash functions. The idea is that you are distributing those rows in a way so that you have in one hash bucket just one record. Otherwise you would have hash collisions, and hash collisions are not really scaling very well. I apply here a very simple hash function. I'm just grouping on odd and even numbers. Of course, in reality, the hash function is just more complicated. Just for demonstration. So 1 is an odd value, 3 is odd value, 5 is odd value, 4 even value, 7, 8, then 7 and 3. Means we have just pre-grouped our data. Normally, as I've said, SQL Server makes sure that we have in one hash bucket just one record. That happens during the build phase, means we are building that hash table again in memory. And in the second phase, in the probe phase, SQL Server takes the inner table, in our case table B, and just probes into that hash table for every record. Value of 2, we apply our hash function. We know a value of 2 is an even value, means we just look in the second hash bucket. If the hash bucket is empty, we have no matching row. If we have a record, we have a matching row. As I've already said, the idea behind the hash function is that we have just one record in a hash bucket. Value of 2, we have no match. Value of 1, we have a match. Value of 5, we have a match. Value of 7, yes. Value of 4, yes. 2, no, and 1. Means that's the result from the hash join. Again, the hash join needs a memory grant for that hash table. And the memory grant is again based on the estimated numbers of rows which are retrieved from the statistics. So when you have a hash join, it's also very, very important that you deal with accurate statistics. Otherwise, the hash join is also spilled over to DempDB like a sort operator. Let's have a look on that. I have here a simple hash join between two tables, the table person and person phone. So you can see in the execution plan, SQL Server performs the hash join. SQL Server has chosen the person phone as the author table because in that table we have only 19,900 rows, and in the table person, well, we have also 19,900 rows, but as you can see, the row size of the other table is a little bit smaller. We have here 45 bytes, and in the other table we have 117 bytes. So also the row size influences the query optimizer which table is the outer table. And you can see, because we have the hash join, we have again a memory grant. In that case, that query needs 8.5 megabytes of space for that hash table that we are building in memory. I just want to show you what happens when the memory grant for such a hash join is too small. I create here two tables. With 1,500 rows. And I'm hinting here SQL Server for a hash join. When we execute, whoops. That was nice. That's nice. I have no idea why we can't produce a query plan with a hash join. Cool. No idea. Wow. Sorry about that. Sorry about that. Really, really no idea. I would have created here a plan with a hash join, and then I would have fooled SQL Server. We have a table with 1,500 rows. Means with a table of 1,500 rows, SQL Server changes our statistics when 20% plus 500 changes have occurred. What we have done was the following. We would insert 799 rows in both tables with the value of 2. As you can see, currently the value of 2 just occurs once. Means we would have changed our data distribution, means estimated numbers of rows from the statistics is still 1, and in reality we return 800 rows. Means the memory grant from the hash join would be the same as previously, but instead of hashing 1 row, you hash during one time 800 rows, and the hash join spills over to DempDB. In that case, our query would take around 1 minute. Afterwards, we have we would have updated our statistics, and when we run the query again, it would run only for 30 seconds because the hash join happens in memory. Just think about that. That's a huge difference, 1 minute versus 30 seconds, when such a hash join spills over to DempDB. But I have really no idea why we got here an execution plan. Okay? So it is very, very important when we have a sort or a hash operator in our execution plan that we have accurate statistics, because that memory grant is always sized on the estimated numbers of rows. Okay? Questions on that? Besides that error message. No idea on that. I think I have shown that example on Monday, and you can prove it worked. Yeah?
Very well.
It worked very well. Yeah? No idea why it's not working now. It worked on Monday. Doesn't help you too much. Okay. First demo that failed for the complete week. Okay. These are the 3 different physical join operators that SQL Server implements. Nested loop, merge join, hash join. Okay, let's move on to the logical level. Now I want to talk on the logical level what happens when we join multiple tables together. The SQL specification itself specifies 3 different join types. A cross join, inner join, and the so-called outer join. When we look on both or on all 3 join types, those join types are just defining which logical phases of a join we execute. Every join has 3 different logical phases. The first phase is a so-called Cartesian product. We're just crossing every record with every record. The second phase is a so-called filter phase, where we are searching for common rows. For example, when we perform an inner join, as previously. And the third phase is called add outer rows, which is implemented by the outer join, where we mark one table as preserved, and on the other table we just add so-called null extended rows, where we have no matching records. And with the logical join operator, you just define which of those 3 phases are happening. Of course, those phases are just happening on the logical level. It wouldn't make sense to make a Cartesian product between 2 tables. Let's say we have 2 tables with 1,000 records. The Cartesian product would be 1,000 multiplied by 1,000, so 1 million of rows, and afterwards to filter those rows. So that's just on the logical level, and SQL Server itself is allowed to make shortcuts as long as the logical result is still the same. So when we make a cross join, we're just crossing every record with every record. So for example, when we say we have a first table with 3 records and we have a second table with 3 records, our result is just 9 records. 1 with 1, 1 with 2, 1 with 3, 2 with 1, 2 with 2, 2 with 3, 3 with 1, 3 with 2, and 3 with 3. A simple cross join. Looks terrible, what we are doing here, and dangerous, but you can do with a cross join amazing things. Let's have a look on that. I have here, for example, in the table sales.currency 105 rows, in the table purchasing random 104 rows, When we make a cross join between both tables, we are getting back 10,920 rows. We're just cross joining every row with every row. When we look at the execution plan, a cross join is always implemented with a nested loop operator. The crazy thing here is that the nested loop has a red cross. Red is always bad. Yellow is always also bad. And SQL Server tells us we have no join predicate. Yes, you are right, SQL Server, but we have explicitly performed the cross join. Okay, so we explicitly requested the cross join, and SQL Server tells us we have here no join predicate. For example, with a cross join, imagine you want to generate currency pairs. You have a table with currencies, euros, pounds, dollars, and so on, and you want to generate currency pairs. You just want to cross every currency with every currency. Very simple with a cross join. The problem is that you have so-called mirror pairs and self pairs. So for example, you have euro with pounds, pounds with euro, and you also have the pound with the pound. We'll see later when we talk about inner joins how you can remove those pairs. Another nice thing about the cross join is you can create with a cross join amazingly fast and simple numbers. You can do amazing things with numbers, as we'll see also later. Imagine the following. I've prepared here a table with all 10 digits. That should be a table that should be part of every database on Earth. So created in the model database. So just 10 digits, nothing more. You can do amazing things. Let's generate 10,000 numbers. We are just cross-joining that table multiple times, and we're just multiplying. So within a few seconds, we have 10,000 ever-increasing numbers. Just think about that. 100,000 numbers. Also not really a problem. So one amazing thing that you can perform with a cross join. Of course, we have here quite a high complexity. So for example, as you can see here, 100,000 numbers, we need already 22,000 logical reads. The whole query takes 280 milliseconds. When you produce 1 million of numbers, you have 10 times more work to perform. As you can see, we have 222,000 logical reads, and the query took 2.5 seconds. Just think about that. So normally, when you are dealing with a larger set of numbers, you should persist them just in a table and not generate them every time on the fly. But very simple. And in the execution plan, you just see that we are doing multiple cross joins between the individual tables that we're referencing here. So another use case where you can make a cross join. Let's skip that one. Questions on the cross join? Who has used by far or up to now a cross join? Few of you? For what things? Test data. Yeah. Yeah, we'll see that later.
Getting all your possible combinations of parameters and this kind of things, and see what different overall sets that you might want to encounter.
Oh yeah, it's also a great use case, yeah. Cool. So I'm not telling you new things anymore. Well, the week is already very old. Inner joins. When we perform an inner join, we perform on the logical level 2 processing phases. In the first step, we create our Cartesian filter, and afterwards we just filter common rows. Imagine in our case, we perform now a join. Inner join, and we say on a.id equals p.id. The first step, we create our question on the logical level, not on the physical level, because that would be variable. And then we just filter common rows. So we have here 3 matches. Just think about that. So we are just intersecting both tables, and we return those rows which appear in both tables. There are also so-called non-equijoin operators. Here, when we say a.id equals b.id, we have a so-called equijoin, the equal sign. When you have not the equal sign, like you say smaller, greater, smaller than, larger than, not equal to, then this is a so-called non-equijoin. It can be also very, very amazingly. And the most important thing here is when you perform a non-equijoin in SQL Server, on the physical level, we always have the nested loop operator. So SQL Server is not able to generate us a plan with a merge join or hash join. With a non-equijoin, we always get a nested loop operator in the execution plan. So let's have a look on that. I have here a simple join, inner join between 2 tables. So as you can see, SQL Server has chosen the merge join as the physical join operator, and the merge join implements on the logical level the inner join. Of course, SQL Server isn't performing here the Cartesian product in the first step and then applying the filtering, because this would be variable. As I've said, this is only on the logical level, and SQL Server is allowed to make shortcuts as long as the result is the same. When we have an inner join, the ordering of our tables doesn't matter. So for example, when we run the same query again, and we use the table sales order detail as the outer table, sales order header as the inner table, SQL Server still produces us the same execution plan and references the table sales order header as the outer table. So the ordering of an inner join is completely irrelevant. It produces the same result. As I've said previously, the goal of the query optimizer is always to have the table with the smallest amount of records and the smallest row size as the outer table. It doesn't matter which physical join operator this is. Nested loop, merge join, hash join, the smallest table is always the outer table, based on the statistics, nothing more. For example, I return here all the customers which have placed orders with us. So what also is very, very important when we perform joins, inner joins, is that SQL Server eliminates rows with null values. So for example, when you have in these columns customer ID null values, then those rows will disappear in the result set. So the inner join only returns you these rows which evaluate to true, means false values, and unknown null values, missing values, are just eliminated with the inner join. That's also very, very important. And you should never ever use the old syntax, where you say where c dot customer ID equals h dot customer ID. The problem with the old syntax is that you can forget the verb predicate. Means in that case we are running a cross join. It takes forever. When we look here on the estimated execution plan, you can see In that case, SQL Server is wide. Nested loop, word cross, dangerous, and SQL Server tells us we have no join predicate. Yeah, now he is wide. And as you can see, we are producing here a huge number of rows with almost 9 gigabytes of data. When you include the verb predicate, you have your inner join. Never ever use that old silly syntax. So that's also very, very important. Let's talk a little bit more in detail about null values. We have in the column currency rate ID, in the table sales order header, some null values. As you can see, 31,000 rows, and we have only around 14,000 rows where we have a non-null value in the column currency rate ID. So we have here around 17,000 rows with null values. Means those 17,000 rows are just eliminated with a traditional inner join. So when we make here the join, we have only the 14,000 rows in our result set. All the other rows are just eliminated through the inner join. Inner join only returns you those rows where the predicate currency rate ID equals currency rate ID evaluate to true. False values, unknown values are just eliminated. Let's talk about non-equi joins. I create here 2 tables and I insert 3 records in every table. As I've already said, when we perform a cross join, we're just crossing every record with every record. So you can see we have here those self pairs, 1 with 1, 2 with 2, 3 with 3, and we also have mirror pairs, 2 with 1 and 1 with 2. When you perform a non-equi join, you can eliminate those self and mirror pairs. Any idea what that thing is doing? Call 1 of table 1 smaller than call 1 of table 2. When you have such crazy things and you don't understand them, look on the logical phases. In the first step, we make our cross join, and in the next step, we make the filter. We say that ID smaller than that ID. 1 smaller than 1, no. 1 smaller than 2, yes. We have a result. 1 smaller than 3, yes. 2 smaller 1, no. 2 smaller than 2, no. 2 smaller than 3, yes. And we are finished. That's our result from that non-equi join. Just think about that. Very simple to understand when you look on the logical phases. First phase is always the Cartesian product. We're just crossing every record with every record, and in the next step, with the inner join, we apply the filtering. Means, as you can see here, we have eliminated the self pairs, and we also have eliminated mirror pairs. So in that case, when we run that, you can see we have 1 with 2, 1 with 3, and 2 with 3. The 3 records that we have found here. Means when you, or let's do another thing in the first step. As I've said, non-equi join is always a nested loop operator in the execution plan. When you hint here SQL Server for another join operator like a merge join or hash join, in that case, SQL Server is not true. Query Optimizer could not produce a query plan. It's not possible. With a non-equi join, you always have a nested loop operator in the execution plan. Other physical join operator is not possible. Means, when we think back to the table currency where we have generated currency pairs, we can eliminate those self and mirror pairs with a non-equi join. As you can see here, we have self pairs, euro with euro, and we have mirror pairs, euro with dollar, dollar with euro. Well, these days it doesn't matter anymore. Euro is almost the same as the dollar. Doesn't matter anymore. So you can see, when we now rewrite that query with a non-equijoin, currency code of the first table smaller than the currency code of the second table, you can see we only return around 4,500 rows, and those self pairs are not found anymore because they are eliminated, and the same is true with the mirror pairs. You have only one pair, euro with dollar. Of course, when you think back to currencies, the mirror pairs would make sense because you have one exchange rate between euro and dollar and one between dollar and euro, which is almost one. Okay? Questions on that? Who has already worked with non-equijoins? Almost nobody. They are very, very rare, but you can do amazing things with them. Okay. Let's continue with outer joins. Let's go to the outer space. With outer joins, we apply 3 logical query processing phases. In the first phase, we make our Cartesian product, like with the cross join. In the second phase, we apply the filter, like with the inner join. And the second phase adds now outer rows. Means when we perform an outer join, we can mark one or both tables as preserved. Means when you make a left join between table A and B, you will get back all rows from table A. And for these rows where you have no matching records in table B, SQL Server adds for the columns of table B so-called null extended rows. When you make a right join, the right table is the preserved one, means you get null extended rows for the left table, table A, and with a full outer join, both tables are preserved. Okay, so the third phase here is to add those outer rows. So we have here left join, means the left table is preserved, right table the right one, and the full join, both tables are marked as preserved. You have also so-called excluding joins, means you can exclude some rows, which we'll also see in the demo. I have here a simple inner join. Returns us all the customers which have a record in the table sales order header, means all the customers which have placed orders with us. Means all the other records from the table customer are just eliminated. When we make now a left join, we say we want to preserve all the rows from the table customer. Means for all the customers where we have no matching rows in the right table, sales order header, we get in those columns that we are referencing, in our case sales order ID, null values. Because the left table, sales.customer, is the preserving one. So you can see here we have a lot of customers which had no orders with us, 701. When you look at the execution plan, SQL Server has chosen on the physical level a merge join, and the logical operation that the merge join here implements is a left outer join. And as you see, the outer keyword is just optional, so a left outer join is the same as a left join. It's the same when we perform an inner join. You can only write join, and inner is just optional. When you change the ordering of the tables, you will get back a different result. That's also very, very important. You can't change the table ordering because now the table sales order header is the preserving one, and we get null extended rows for the table customer. So that's also very, very important. But the query optimizer can make amazing things. How can you swap with that left join both tables? Imagine our statistics are telling us in the table customer we have less records than in the table sales order header, and we want to reference the table customer as the left outer table. How can we reference the table customer as the outer table? What do we have to do in the execution plan? We can change the ordering of the tables when we also, sorry? When we switch the left join to the right join, as you can see here. In that case, Query Optimizer knows from the statistics the table customer has 19,800 rows. The table sales order header has 31,000 rows. So in that case, we want to have the table sales customer as the outer table and transform the left join to a right join so that we can swap both tables. So a left join between table A and B is the same as a right join between table B and A, which the Query Optimizer can use internally, just to swap both tables.
Is the optimizer clever enough to do that without you telling it?
Sorry?
Is the optimizer clever enough to do that without you even telling it?
He will do it, yeah. The Query Optimizer itself implements internally so-called rules. And there's one rule called join commute, and that rule just defines that. When we have an inner join, the ordering doesn't matter. When we have a left join, we can transfer or transform the left join to a right join and vice versa, when we also change the ordering of the tables. And again, the goal is to have the smallest table as the outer table of every physical join operator. And the Query Optimizer implements around 400 different rules. That's just one rule that the Query Optimizer can apply. Means when we write that query as a right join, we get a left join. Okay. We can also perform a full auto join, means in that case both tables are just the preserving ones. As you can see, with a merge join on the physical level, logical operation is a full auto join. Means you can have the null extended rows in both tables. Here we have only the null extended ones on the table sales order header, because when you have one record in that table, you have to have a record in the table customer. You can also make excluding joins. In that case, we are just interested in the null extended rows from the right table. A so-called, where we were here, a so-called left excluding join. So we have only these customers for us in front of us which haven't placed orders with us, the 701 that we have seen previously. In the execution plan, SQL Server just performs a traditional merge join, left join between both, and then we have an explicit filter predicate where we just filter for those null extended rows. Let's try something else. What do you think about that SQL statement? We are interested in the rows where the customer ID is not null in the right table. It's an inner join because the verb predicate eliminates the null extended rows. Just think about that. When you look at the execution plan, we have an inner join. Wouldn't make sense to make a left join and afterwards with the filter we eliminate the null extended rows. That's just work which is useless. Just think about that. Sometimes we are just writing our queries too complicated and the query optimizer is able to simplify that query for us. Query optimizer looks at that query and thinks, okay, you are a complicated person. In reality, I can produce you and give you the same logical result with an inner join. Doesn't make sense to make a left join, add null extended rows, and then filter those null extended rows from the result set. So query optimizer, the most intelligent person or thing on earth. Let's call it thing. Here I have a white excluding join, auto excluding join when we work with a full auto join. In the execution plan, same thing as previously, SQL Server performs the full auto join and then we have the explicit filter. Let's combine a few things together. Imagine the following. We have an orders table and we want to know all the days where we had no orders. How can you achieve that result? You have already seen everything, otherwise it wouldn't be fair.
Use your numbers table to give you a set of days and then do an outer join against your orders table.
Yes. So in the first step, we have to generate a time axis. Let's use the numbers table. Let's recreate it. I create another temp table. In that table, we will persist afterwards our records. So I'm just inserting here 10,000 rows, 10,000 numbers with the cross join that we have seen so far. So we have persisted them, 10,000 or even 100,000. And in the first step, we need a time axis. Let's use the numbers table. So what I'm doing here, with date diff, date add, I just generate, let's say, a time dimension from the 1st January of 2005 up to the last day of 2005. Very simple. Just think about that. Amazing things that you can do with 10 digits in a database. This table is now the left table in our left join to our orders table. And we join on the date column. Means when we have no order, we get a null extended row on the right table and we just filter on those null extended rows. Means we have found the orders or the dates on which we haven't placed an order. Very simple. So we make the left join to the table sales order header and we just filter on the null extended rows. So we have here 184 rows in 2005 where we haven't placed any orders. Nice. And now tell me, how large is the gap? As you can see here, we have from the 1st January of 2005 up to the 30th of June, no orders, so we have a gap of 180 days, and then we have here one order in August, another order in September, and another order in October. Tell me how large are those gaps with the SQL?
Take that data set, join it back to itself for the second put a constraint on it so that you're looking for the minimum value from the second data set.
Yeah.
It's greater than your current
Mm-hmm.
row that you're in the first data set.
So we have,
Just do a minus.
Yeah. So we have multiple ways how to perform that. The easiest way is you need to reference your previous row. And then you just make a subtraction. When the subtraction is 1, minus 1 equals 0, there is no gap. So the question is how you can reference the previous row. There are multiple ways with a self-join. The problem is it is not very fast because it has an exponential complexity. You have to run that self-join over and over and over and over again. The other way is to work with windowing functions that we have seen on Monday with lead and lag. I'm using here the windowing functions. So as you can see in the first step, I have here a derived table, which is just our original set of rows. And then with the windowing functions lead, which was introduced in SQL Server 2012, we can retrieve our next order date. As you can see, when we run that now, we have here our next order date, and I have also calculated the difference between the order date and the next order date, minus 1. Okay? So we have here that difference, and then with that result, we just check where the difference is larger than 0. Takes a few seconds, and you have these intervals where you had no orders. Just think about that. Who of you knows Itzig Ben-Gun? Oops. Now come on. Itzig Ben-Gun, a guru in T-SQL. His brain mainly thinks in T-SQL. Just Google for him and gaps and islands. Means you have data, and in that data you want to identify gaps and you want to identify islands. For example, imagine you want to know when your users were online. You want to identify islands. You want to know when your users were offline, gaps. You want to know from your employee table when employees were on vacation. How often, how long they were on vacation. The same thing that we have done here, just in a different perspective. You can do amazing things with that. And he has written a lot of information about it, and also just different ways how you can accomplish the same logical result in different ways, and which way is the better one regarding performance. When you read those white papers, you need some coffee and time. Another problem is also from Itzig Ben-Gun. The minimum missing value. Imagine the following, a simple table. I insert some rows, and I want to return the minimum missing value. As you can see here, we have a value of 1, 2, 3, 4, 5, and 9. Means in that case, the value 6 is our minimum missing value. How can we find that value? With a left join against the table, and referencing in the left join the next record. So as you can see here, make a left join on that first column plus 1. Means we reference our next record. Of course, in that result set, we have two null extended rows. The null extended row for the value of 6, which is our minimum missing value, and also for the last row, because the value of 10 doesn't exist in our result set. Means we just restrict on the null extended rows, and we just take the minimum plus 1 to get the minimum missing value, 6. You want to know from your orders table what was the first day in the current year where we had no orders. Make a left join plus 1 on that order state column and restrict on the minimum value plus 1 is your minimum missing value. So again, a very, very powerful concept. What I'm doing here, I'm calculating the size of the largest gap. For example, with a row number calculation. So in that case, our gap between 6 and 9 was 3. Imagine you want to identify the largest period in your orders table where you had no orders. In that case, I have just generated a row number, which is again part of the windowing function, and I have just subtracted the current value. Means you can see with the last record we have here a gap of 3. And on that, this is a so-called grouping factor. We have performed the group by aggregation and just returned it, where the grouping is larger than 0. In that case, it's our minimum, it's our largest gap of 3. Just think about that. So just different amazing things that you can do with joins, windowing functions in SQL Server in the context of gaps and islands. You can also make this a little bit or in a different way, for example, with the lead windowing function, which was introduced with SQL Server 2008. 2012, sorry, 2008. 2012, okay? Just another way how to achieve the same logical result. Questions on that? You are so silent.
And the lead and lag operators, are they, the way they've been implemented, are they quite efficient?
They are quite efficient, yeah. But they are only available since SQL Server 2012. But even on SQL Server 2005 and higher, you can make use of the windowing functions to retrieve the previous and next row. You just say rows between one preceding and one preceding is your previous row. Rows between one following and one following is your next row. Since SQL Server 2012, it's just easier with lead and lag to retrieve the next and previous row. Perfect. Let's talk now a little bit more about subqueries. It seems that subqueries doesn't correlate to joins, but when we look at the execution plan, you will see that subqueries are also executed with a physical join operator. Therefore, I have included them here. When we talk about subqueries in SQL Server, we have different kinds of subqueries. We have a so-called self-contained subquery, which is just a separate subquery which can execute it independently, so very, very easy to understand, very easy to debug. On the other hand, we have so-called correlated subqueries, means the inner query has a dependency to the outer query. Means from a logical perspective, the correlated subquery is executed for every row from the outer query. But as we will see here, the query optimizer can do again amazing things. It doesn't mean that the correlated subquery has to be executed for every row on the physical level. We just specified that on the logical level. So as I've said, self-contained subqueries, very, very easy to use, can be used everywhere where SQL Server expects a scaled expression, like in a var, in a select, and so on. We also have so-called multi-valued subqueries, which we can use in combination with an in, not in, between, and so on. Let's have a look on them. They are very, very simple. So for example, I declare here a variable to get the maximum sales order ID and reference that variable in my select statement. You can make it easier by just specifying the maximum sales order ID in a self-contained subquery. Self-contained means we can execute that independently without executing the outer query. On the logical level, we have referenced our table sales order header multiple times. In reality, SQL Server just scans from that clustered index once and just retrieves the first row from that clustered index with a backward scan. So very complicated written. It's the same when we say, for example, select top 1 from sales order header, order by sales order ID descending. Gives us this, whoops, star. Gives us the same result with the same execution plan. Okay? Just written a little bit more complicated. Minimum gives you the same execution plan, only with the difference that the scan of the clustered index is forward instead of backward. When you are dealing with a scalar-valued self-contained subquery, it's very, very important that you just return one value, otherwise you get the famous error message in SQL Server that everyone has already seen multiple times in his or her life. Okay? Multi-valued subqueries can be used in combination with an in predicate. We are interested in some rows, like all the orders which were done by the salespersons which are in the territory Northwest. And as you can see here in the execution plan, in that case, SQL Server performs a nested loop. So that in is just on the physical level a nested loop, nothing more. The nested loop that we have already seen previously. Not in is just a negation of it. When we look at the execution plan, we have now a so-called left anti-semi-join. A semi-join in SQL Server is a half join. So we are just doing the half of a join. Imagine, for example, football, a semi-finale. It's the same here, a semi-join. With a semi-join, we are only interested if we have matching rows or not. We are not interested in how those rows looks like. We just want to know if we have matching rows or not. Therefore the name semi-join. We just probe and check for the existence of rows in another table. And an anti-semi-join is just a negation of it. Means in that case, we return only the records when we have here in the other table no existing matching rows. An anti-semi-join in SQL Server. And here it's a left anti-semi-join, means the left table is again the preserving one. You can also have a right anti-semi-join or a right semi-join. A few words about correlated subqueries. As I've already said, On the logical level, a correlated subquery is executed for every row that we return from the outer table. On the physical level, SQL Server can do completely different things in the execution plan. Semi-join, as I've said previously, we just check if we have some rows in another table. We're not interested in how these rows looks like. We just want to know the fact if we have matching rows or not. If we have a matching row, then we return that record. If not, we discard it. And an anti-semi-join is just a negation of it. Means when we have no matching rows, then we return the record from the other table. If we have a matching row, we will not return it. Let's have a look on that. I have here, for example, a correlated subquery. Correlated subquery means I have here a reference to a column from our outer table. Means in that case, we can't run that subquery anymore because we have a correlation to the outer table. Means in that case, logically, from a logical perspective, we execute that query for every row that is returned from the outer table. So when we run that, and when we look, of course, at the execution plan, you can see we have here an inner join on the logical level and a hash join on the physical level. And because of the hash join, we again have a memory grant of 9.1 megabytes. Let's skip over that. For example, I have here a subquery, a correlated one, which just calculates a percentage value of every record that we have here. When we look at the execution plan, again, it's just a physical join operator. In our case, a hash join between both tables. Okay? So you can already see with subqueries in the execution plan, you mainly again deal with a physical join operator, nothing more. Nested loop, merge join, or hash join. For example, previous next value. You can also calculate them manually. For example, your next value is the record, the minimum record, where your primary key is larger than the current key. Just a different way how to retrieve the next record. The previous record is the maximum record where the primary key is smaller than the current one. Of course, this approach is very, very slow, but you are able to achieve the same logical result without any windowing functions. As you can see here, that's our previous value. Whoops. And we have here our next value, just with a correlated subquery. In that case, we have here nested loops. Normally, when you look on those nested loop operators, you can already see, just from the big picture, that's not really good, because normally you should have on the outer table just a few numbers of records. As you have seen, we use here a non-equijoin, means SQL Server has to use a nested loop. And you can see we have on the table sales order header here a scan count of over 60,000 with more than 203,000 logical reads. So never ever do that. Use windowing functions, it's much more easier. But when you want to train your brain, you can also try it to achieve the same logical result with traditional SQL statements. Okay, questions? Perfect. It's too late, sorry. No, just kidding.
Just in regards to filtering.
Sorry?
On your very first slide, you showed the query, the join and then filtered after it.
Yeah.
Are there any circumstances where SQL is a bit more clever about that and might actually filter on a table first before it does the join?
When you have an excluding join, the filter is always after the auto join. When
So
you...
If you've got two tables with a million records,
Yeah.
and the filter might actually
Yeah.
reduce it down to 10,
Yeah.
and do a join on a million tables.
Yeah. In the first step, you always have the left or right join, so the auto join. So the filter always happens later, which is from a performance perspective not really the best one, but you can't do it in another way. Because in the first step, you have to identify the null extended rows. You have to generate them. Means you have to perform the left or right join in the first step, so that you can afterwards filter them. But you have also seen when you're excluding those null extended rows, then the query optimizer is smart enough to transform your outer join to an inner join. But when you filter on those null extended rows, then the filter is always after the outer join in the execution plan. Yeah.
In that same example, would you be able to do a join on a subquery and fill it out first? If you had like a million in each table, you did like a select sketch 10 rows,
Yeah.
and then do a join after to the other table,
Yeah.
rows. Would that then have the performance benefit, or would you still have to do the join either way?
I have to check that. Can't say it out of the head. The easiest way, just try it. Just try it and just compare both execution plans. Which is faster? Normally, as I've already said on Monday in my pre-con, the nice thing about SQL is, and SQL Server, that you sometimes are able to write your logical SQL statement in different ways, and the query optimizer compiles you the same physical plan. Sometimes you have to write your SQL statement in different ways, and the query optimizer compiles you a different execution plan. As we have seen earlier with a top 1 and a max or min, depending on the sorting order, you are getting the same execution plan. You have just written your logical query differently. And in other cases, you also have to influence SQL Server a little bit more by writing your logical query in a different way to get a better performing execution plan. So SQL itself, the programming language, is really, really complicated. Because it's just a declarative language, and you just specify how your result should look like. Okay? Perfect. So in the first step, we have talked about the physical join operators. We have covered the nested loop operator, merge join, hash join operator. Then we moved on to logical joins. We have covered cross join, inner join, and outer join. As I've said, on the logical level, we just specify which of the 3 logical phases we are applying. First phase is always a cross join, followed the Cartesian product, followed by the filtering phase, followed by the null extended, by adding the null extended rows. And with the join operator itself, you just specify which of those 3 phases should happen. And finally, at the very end, I've given you a short overview about subqueries, because you have seen in the execution plan, when you execute a subquery, you mainly work again with physical join operators in SQL Server. Perfect. How do you have enjoyed that session? Cool. If you want to know more about SQL Server, mainly performance tuning and troubleshooting, I'm coming back to London in the first week of June, where I run my SQL Server performance tuning workshop, 5 days entirely about performance tuning and troubleshooting on SQL Server. You can find further information about that workshop on my website. If you mention that you have attended one of my DevWeek talks, I can also give you a discount of 10%. Perfect. So thanks for attending and enjoy the rest of the conference. Thank you.